Hey, we're live. Hi, Verge.
Hi, Mark. Welcome, everybody, for our Friday lesson here at AP Live. So let's get started.
I am Mark Corrali from Ryan High School in Denton, Texas.
And I'm Verge Cornelius from Lafayette High School in Oxford, Mississippi. Go Doors!
All right. If you've been here, you're getting tired of this slide. If you haven't, welcome to this slide. It's our schedule for the remaining few weeks up until May 1st. Come back, pause it later, take a picture of that QR code or write down that bit.ly, and those will take you to this calendar. You can also go to the Dropbox, which we'll give you later.
But if you just join us every day, there's no need to know what the schedule is.
That's right. Just be here anyway.
Just be here anyway. Yeah.
That's what we do. Anyway, AP Coronavirus Updates.collegeboard.org has the, if you want to go see the details on the exam, there aren't many. It's a 45-ish exam, 25 minutes FRQ followed by a 15-minute FRQ.
And I should say too that they will be posting videos that we'll let you know about that, but look for some videos that will help you to understand how this platform is going to work.
Oh no, and it looks like I got a graphic out of place, but we're going to go with it anyway.
Okay.
Oh, yes, we do. Look at that. Oh, disaster. Oh no. So we did such a good job on the FRQ, Verge. On the FRQ, we even had this quote. We went back, we looked, we said, hey, units are asked for, so let's put the units on there. But on the first document with the notes page, units were asked for on that one that ended up with a secant squared tangent, and neither one of us caught it, and a teacher in Houston did, and so thank you. And we'll start the counter again Monday, we hope.
Oh, was that the one where it was like 4/3√3 or something like that for the answer? Okay,
and it did
shout
say
out to that teacher who caught it. And
it did say indicate units, and we did not.
So. Yep, my bad. That was my fault.
Yeah, but my job's to check you. So
true. Okay.
All right. So here we are. We're going to start our warm up in a little bit. We've got a long time still. It's 3 weeks from Tuesday. We'll be here fast, but as we go every day, each day is going to be its own day, right? So we're going to wrap up this week, kind of do a mixed bag review of these first 4 units, and then we'll wrap up and let you know what's in the Dropbox. And that Dropbox is populated already. Also, before I advance the slide, Wednesday's key is in there. So whatever it was that we did Wednesday, was that chain roll? Yeah.
Mm-hmm.
All right, so here's our warm up. There's a lot of text. So, this is a particle moving along a straight path, and its position is modeled by moving along a straight path, and its position is modeled by the function s of t equals the natural log of t, measured in yards on the interval 1 to 9, where t is measured in minutes. Find each of the following and indicate units of measure.
Let's see if we can do it this time.
And we put it there before we got the email. We know it's important. Hey, but you can miss a point, still make a 5. I feel confident.
That's true. Or 4 or 3.
Yeah, that's right. What 90%'s an A for a reason. What is the average velocity of the particle on the interval from e to the 1/2 to e squared? What is the velocity of the particle at time t equals e squared? And what is the acceleration of the particle at time t equals e to the 1/2? And I'm going to switch over to my camera.
And I might tell a joke while he's doing that.
Go ahead.
What do you call a man who spent all summer at the beach?
I think I alluded to this one already in one of our presentations.
I think you did too.
So what do you call?
Sent me this.
What do you call a man who spends all day in the summer at the beach?
All summer at the beach. You call that man a tangent.
And if he has anything covered up, those are tangent lines, right?
Yeah, love those.
Okay, so what is the average velocity of the particle? I am going to go ahead and copy that s of t back down. It was the natural log of t, and t's in the interval bracket
1 to 9.
1 to 9. All right. So I could go find the velocity formula and use the average value function, which is in unit 8, which isn't tested. So you're like, hey, this isn't tested. But velocity is the rate of change of position So they're asking for an average rate of change. Talked about bells going off in our heads the other day. Average rate of change to set off a bell in my head. What do you think that is?
For me, just slope of the
That's
secant
the
line.
so that's just the slope of position. And I have a position formula. So I want to do s of e squared minus s of e to the half over e squared minus e to the 1/2. Oops. Got a little negative snuck its way in there. All right, so that's my average velocity for this interval. I didn't really plan out my space well, so I'm gonna kind of do what Verge did yesterday.
Yep.
S of e squared will be the log of e squared minus the log of e to the 1/2. And the denominator, I'm just going to leave the way it is. I'm perfectly happy with e squared minus e to the half on the bottom.
Me too.
Log of e squared, well, you can do it a couple of ways. You can bring the 2 down front using properties of logs, and then log of e is 1. Or what natural log is asking you, what is the exponent on e to get this? Well, what's the exponent on e to get e squared? The 2.
2.
What's the exponent on e to the 1/2 to get e to the 1/2? 1/2. And of course, that e to the 1/2 can be read a different way, can it?
Square root of e.
Yep.
But
and of course, you can stop here. That is a perfectly awesome numerical answer. But then often you'll see it, you go look in the back of the book or a multiple choice, and you might see something with the 2 distributed through the denominator. So, I was going to say something else about that, but
just units of measure.
Units of measure. Let's indicate units of measure. We are measured. Let's see, back here we said we have yards and minutes. So this was yards, this was minutes. So if I really wanted to just get my nice concise answer, yards per minute. I think that covers it.
Yep.
Yay. And I'm gonna, here's your recycling. Yeah, just do that. Okay. So what's the velocity of the particle at time t? So how is this question different than the first one, Verge?
Well, it didn't say what kind of velocity, but it did say at time t equals e squared. So it's happening at a moment in time instead of over an interval. So we have to be talking about the instantaneous rate of change here, the instantaneous velocity, even though it's not explicitly asking for it. So this has to be the derivative.
Awesome. So yeah,
it's as if we plan to say these things.
I know, right? We do, but we don't plan who's going to say them. So
right,
there's a little. All right. So I need v of t, which is s prime of t, which is 1 over t, because my s of t up here being the natural log of t, the derivative is just 1 over t. You'll have to excuse me for a second. There you go. Sorry, my dog was being very patient, but trying to wait to get through a door. So we've got, and so I want v of e squared, 1 over e squared. That's good. That's done. Except
units of measure.
Units of measure. And this is actually ds dt. If I want to do my unit, s is in yards, time is in minutes. So yards per minute, because both velocities should probably have the same units.
Can't think of an example where they wouldn't, given the same position function.
You could do a conversion, I suppose. You could.
Oh, maybe.
Yeah, I could convert that to feet per second if I wanted to, but
yeah, true.
Don't be that kid. All right. All right. So acceleration, Verge.
That would be the derivative of the velocity.
Yeah. So now I need my derivative of that. Of course, you don't have to label all of these, but you should make this connection on a free response. You want to make that connection on a free response. If you do a derivative or an integral, you should always show the setup. It is a calculus exam. All right, so v of t was 1 over t. That's t to the -1, so negative t, -1 minus 1 to to the -2 or -1 over t squared. Of course, a lot of you will make that jump straight from 1 over t to -1 over t squared. And this then becomes a of e to the half, e to the half square. And e to the half squared is just e, right?
Mm-hmm. Power to a power, multiply the
And
exponents.
this is 2 derivatives of position with respect to time twice. So 1s yards time twice per minutes squared.
Mm-hmm.
And I think I did okay.
You did great.
All right. So that's kind of our warm up on that. And then
And yesterday we said that as Mark's getting organized, we said we were going to lead off with that potato problem.
yes.
So that is what we are going to do next is that lovely potato problem, or Mark's going to do it.
Coming in, sorry.
Yep. And then we're going to do another related rates question. And then we're going to talk some about Lobethal's rule.
Yeah.
As you kind of saw him.
You saw a little preview of the sheet there a second ago.
The preview of Lobethal.
Yes, that's about the extent of my French. The Pepe Le Pew French. All right. So at time t equals 0, a boiled potato is taken from a pot on a stove and left to cool in a kitchen. I'm sorry, 7 times. The internal temperature of the potato is 91 degrees Celsius at times t equals 0, and the internal temperature of the potato is greater than 27 degrees Celsius for all times t greater than 0. The internal temperature of the potato at time t minutes can be modeled by the function h that satisfies this given differential equation, where h of t is measured in degrees Celsius and h of 0 is 91. My comment about 7 times was the phrase internal temperature of the potato occurs 7 times in this problem. Write an equation for the line tangent to the graph of h at t equals 0. Use this equation to approximate the internal temperature of the potato at time t equals 3. So, equation of a tangent line. Even if I don't even underline tangent, what do I need to do to find the equation of a line?
You need a point and you need a slope.
And I need a slope.
And I think you were given a point.
I was given it twice. They said
at
the beginning at time 0 it's 91, and then they even wrote it as a function down here in function notation. So we have 0, 91. And slope, I have a formula for the slope, right? In terms of
what
h.
should you plug in for the variable, the 0 or the 91?
Yeah, well, this is h of 0, so that means that's t, and that's h.
Yep.
And 91 minus 27, I believe, is 64. And so that's -1/4 of 64, or -1/16. Of course, you could leave the slope like that, but yeah.
I don't think it's -1/16, Mark.
Nope. What did I do wrong?
Well, isn't the 64 in the numerator?
What I meant to say was the reciprocal of -1/16.
Yes. I should have let you go just a little longer for all the teachers out there to be having heart attacks.
See that 30-second delay till my texts start blowing up. All right, so here's my tangent line.
Now you're trying to freak him out again, Mark.
I was not there. I added y0 to the right. Either get used to this form of the line or...
Okay, I'll let you figure out your own mistake.
Oh, there's an M. If you'd be quieter, this would be a lot easier. All right, so it's Friday, folks. Welcome. As the viewership numbers on YouTube plummet.
I think last Friday is when we lost you, Mark. So let's not jinx anything.
Oh, that's true. I still have my PowerPoint running in the background. I want to close that because I still think that's what crashed it. All right. Okay. Anyway, so assuming I multiplied 16 times x correctly. This is my equation of my line. I use my y0 is my h, right? This is my y0 and my x0 as well over here. And I have this equation of my line. So That's my tangent line. And then h of 3 is going to be approximately 91 minus 16 times 3, which of course you could stop there, or we can keep going and 43. Yeah.
Excellent. And you could stop at that tangent line too, above where the box is.
Yeah. Yeah, and you can start, and then negative 16 can appear like this if dividing 64 by 4 is difficult, like it was for me. Good example of why maybe we should have stopped. But yeah, you can leave it very robust, but
and you don't need units of measure on that one either,
No.
because it wasn't requested. Lucky for us.
Yes. All right, so let's see if I can get through this one without making anything silly. So we're going to use the second derivative to determine whether your answer in part A is an underestimate or overestimate. This is part of what we're reviewing next week, but that's okay. We're going to continue. Of the internal temperature of the potato at time t equals 3, because finding that second derivative definitely falls under what we did this week, because we are going to take the derivative of that, of the dH dt. And the negative 1/4 is along for the ride. It's just a constant multiplier. The derivative of h is 1, but we're taking it with the derivative of t. So a dH dt shows up, minus 0. And dH dt is the thing I started with. And it looks like that's going to be 1/16 h minus 27.
Go ahead and push it up just a little bit.
Thank you. Sorry. There we go. And they did say up here that for any time greater than 27, that the temperature is always greater than 27 degrees. So I know this is always positive. I also have 43 was my estimate, so I'm pretty sure that's going to be a positive value. And second derivative positive, this is a little bit of review from what we're supposed to be doing next week. But what does that tell me about the shape of the graph of h, Verge?
So if the second derivative is positive, then you know that the shape of the solution curve would have been concave up in that area, like in that, on that interval. So that means the tangent line is riding underneath the solution curve on that interval, which means that the tangent line is providing what Mark said, an underestimate.
One of our definitions of concavity is if it is concave up, the curve is always above the tangent line. And if it's concave down, the curve is bending down from the tangent line. So that's another way to keep those straight. So since we're bending up from the curve, or up from the tangent line will always be under the curve.
Great.
All right.
And then that's a really nice free response question. The next one we're going to do is another one that involves a related rate, the one with the funnel. If you're kind of looking at the Dropbox, that one with the potato is actually in yesterday's Dropbox, whereas the funnel is in today's Dropbox. Am I right about that, Mark?
Yes, that is correct.
Okay. So we forgot to say that earlier for those of you who are just joining us for the first time today, but you'll figure it out.
You can always pause.
Yeah, that's right.
So am I doing the funnel?
Yes. And then I'll go ahead and do the Lobethal.
Oh, man. Okay, yeah, Calculus the Musical's version of that song is so wonderful. All right,
and I have it recorded.
Oh, I have the soundtrack on CD.
Nerd alert!
I've seen them 3 times live.
Oh my gosh!
The inside of a funnel of height 10 inches has a circular cross section, as shown in the figure above. At height h, the radius of the funnel is given by this equation for r, where h is between 0 and 10. The units of r and h are inches. And we're jumping straight to part C. A and B had other things going on from unit 8, and which is volume and that. But C is right in our wheelhouse for this week. The funnel contains liquid that is draining from the bottom. So right down there at that little hole. At the instant where the height of the liquid is h equals 3 inches, the radius of the surface of the liquid is decreasing at a rate of 1/5 inch per second, 1/5 of an inch per second. At this instant, what is the rate of change of the height of the liquid with respect to time? And I'm going to start over and read backwards. Rate of change of height with respect to time. So they want dH dt. The radius of the surface of the liquid is decreasing. So dr dt is negative 1/5. Of course, h is 3 inches. These all have units, but that's just to remind me later. And we know r. So I know 20th. And they want dH dt. Well, I have an R here and an H here. I think I can solve this for dH dt. I know stuff about R and H, right?
Yeah, if you differentiate, both of those are differentials are going to pop out after you
And
differentiate.
they didn't tell me R, but as soon as I take that derivative,
it doesn't matter what R is.
Again, 1/20th is a constant multiplier. You could distribute that and call that 3/20ths plus 1/20th h squared. And then the 3/20ths will go away as a constant. And so you'll end up at the same place, right? Because this will be 0 plus 2h dH dt. Again, 2h to the 1. But keeping in mind, and you don't have to write this down, but it should be on your head that you are taking derivative with respect to t. So when it's not a t, you have to do that chain rule. And now I'm just going to go ahead and start plugging in stuff I know. Right? This is negative 1/5, 1/20th, h is 3, and dH dt is the big question mark. That's what I want. Oh, this looks awesome. So, how fast of a jump do you want to make, right?
These kids are good. They can do it.
Question is, can I?
Yeah, you can.
I mean,
okay, that's fine. Leave it there.
Yeah, exactly. Just, and done. Except units. So, and I don't think this even asked for units, but I'm still going to go. That's still inches per second. What is it? Is it negative 2/3?
I think so. Let me look back.
20 times 5 is 4. 2 times 3 is 6. Yeah.
Let's see. Well, I don't know why I can't find it.
It's okay.
It's negative 2/3. Okay, I believe you. Yes, there it is. Inches per second. Yep. Okay, you got it. All right. Awesome. Those are some of my favorite problems in the whole wide world. I can't believe I didn't insist that I do them, but okay. So Mark and I have this big debate all the time. And it's pretty funny because we, I'm going to go ahead and steal a screen, Mark.
Yeah.
We send each other stuff that we don't edit, send them PDF. But he has something that he can just go ahead and like undo the PDF anyway. This is what you got. I'm good. With Lobethal's rule, and this little notes page is in your is in that shared folder. But with Lobethal's rule, sometimes you see this mathematician's name with the OS, the way I have it, and sometimes you see it with the circumflex, which would be like this, just to learn a little bit of French. Okay.
Scoot down just a little bit.
Yeah. I don't know for sure how it would have been spelled, or both conventions would have been fine. And we can talk for a long time about who this rule is actually attributed to, but in any case,
you paid good money for it. We'll just leave it at that.
Yeah. In any case, this is a great application of the derivative, because it's if you have a function, sorry, if you have a limit that's in an indeterminate form like 0 over 0 or infinity over infinity, okay, if that's what the ratio is showing you when you're trying to figure out and evaluate a limit, then Lobethal's rule will apply. And I kind of gave a little bit of airtime to it yesterday. We did limits on Monday. So now it's time to really kind of get into Lobethal's rule a little bit more. And this is going to be our last bit of Lobethal's rule. We're going to go ahead and see it again next week with fundamental theorem. So it's going to get excellent. But basically what it says is that if the limit as x approaches a of the numerator f of x is equal to 0, and the limit as x approaches a of g of x is equal to 0, then this limit here of the quotient is equal to the limit of the derivatives of each of the individual numerator and denominator. This is not quotient rule, so you have to kind of, keep everything straight in your head. Same goes as it holds true if you're approaching plus or minus infinity as x approaches a. So, either of these situations. In any case, let's take a look just at a few examples that are nice examples for a variety of different reasons. But this first one here, evaluate the limits, use Lobethal's rule only if it applies. Limit as x approaches 0 of sine 2x over sine 5x. Well, let's look at that numerator. The limit as x approaches 0 of sine 2x is equal to sine of 0, which is 0. And then the same thing holds for the denominator. The limit as x approaches 0 of my denominator is also ending up to be 0. So we have this indeterminate form here of 0 over 0, so Lobethal's rule applies. So I can go ahead and take the derivative of the numerator, which would be cosine of 2x, but then times the derivative of what's inside. So you got to do a chain rule, so 2. And then divided by derivative of the denominator, which would be the derivative of sine 5x would be cosine 5x. And then times the derivative of what's inside, so times 5. So then what you do after you apply Lobethal's rule once, you try that direct substitution again. So you substitute in 0. 2 times 0 is 0. Cosine of 0 would be how much?
1.
1. So we have 1 times 2 over another 1 times 5, so 2/5. If you wound up with an indeterminate form again, you could apply Lobethal's rule again. You could continue to apply Lobethal's rule. Sometimes you kind of get stuck in the weeds and you think to yourself, this is not working for me. I need to have a different way to analyze this. But sometimes 2 or 3 applications and it works. So go ahead, Mark. Were you going to say something about that?
No, I was just going to add, if you do get that indeterminate form again, because a lot like what you did where you substituted the 2 and the 5, it's really natural to do. You don't want to ever write equals 0 over 0 because it's of that form. But we have a magic power on the AP test. If you draw a line through it, that's the same as erasing it never existed. So if you write it, it's not the end of the world. Just cross it out and then write what you need to write to continue.
What Mark is saying is you don't want to do this. This is wrong.
Because you're right now, she's saying that's equal to 2/5 because later on you say it's equal to 2/5.
So don't ever use notation like this. Notice how I said that my numerator was equal to 0 as x approach 0, and same with my denominator. So on that direct substitution, you just got to be careful.
Yeah, but
that's going to come up in example 2.
Yeah, my from a testing standpoint, it's so easy to do the substitution and write it. And if you don't have an erasable pen like Verge has or she provided for her friends, you can't just draw a line through it and then it's gone.
I'm actually going to do number 3 next. If any of my students are watching, they're like, they're going to say something like, well, that's what she always does. She never goes in order. So here I have the limit as x approaches infinity of the natural log of x divided by 4 square root of x. So one more time, because I know my connection gets unstable sometimes. Limit as x approaches infinity of natural log of x divided by 4 square root of x. This is of the indeterminate form infinity over infinity. If you substitute an infinity here to the natural log of infinity is infinity. It's getting there very slowly, but it is getting there. Same thing here, 4 times the square root of infinity is going to end up being infinity. So I'm going to say, you know, I don't know. I'm going to go ahead and be very, very careful mathematically here. Can I say that, Mark?
Yes, because that's it's a specific way of saying does not exist.
Mm-hmm. And so therefore, 3 little dots, I usually say this, Lobethal's rule applies. That's not necessary, but that's just what's happening in my head. So now I'm going to apply Lobethal's rule. I'm going to take the derivative of the numerator. Derivative of natural log of x is 1 over x. Derivative of the denominator is going to be 4 over 2 root x. And then I might need to do a little bit of algebra here before I go ahead and substitute in again, because I can already tell substituting in here, I'm going to get 0 over 0, and that's going to get me another L'Hopital's rule situation. So in terms of, I'm going to just go ahead and do my little side bubble here, 1 over x times, and then the reciprocal, 2 root x over 4. So I'm multiplying the numerator by the reciprocal of the denominator. I get root x over 2x. Does that look right, Mark?
Yeah, reciprocal. Yeah, I think you're good.
Okay, and then so I end up with 1 over 2 root x, because root x divided by x is just x to the 1/2 divided by x to the 1, and so we end up with a square root in the denominator. So that's a little bit of algebra to rewrite this quotient. So now I have the limit as x approaches infinity of 1 over 2 root x. Now this does need 0. Why? Because I'm taking the number 1 and I'm dividing it by infinity. 2 times the square root of infinity is gigantic. So that approaches 0. Basically, you have 1 divided by a huge number. If you want to think about it numerically, you can think about it graphically too, because you can think about like what's happening on that asymptote or whatever.
Right.
But that's going to end up being 0. So let's take a look at this one next. And if I did that one too quickly, just rewind and pause it and take a look at the algebra there. This says the limit as x approaches 0 of the square root of x plus 1 minus 1 minus x over 2, all divided by 5 squared. Well, I can definitely pretty easily see that the denominator there, when I substitute in 0 to the 5x squared, I get 0. And then the numerator, let's see, 0 plus 1 is 1, square root of 1 is 1, 1 minus 1 is 0, and then minus 0 divided by 2 is 0. So the limit, here's the clever thing to write.
Yeah, the
limit
0
is
sandwich.
the limit as x approaches 0 of this numerator, if I can write it down correctly, is going to be equal to 0 as well on either side, you know. So therefore, L'Hopital's rule applies. So I need to take the derivative of the numerator, the derivative of the denominator, and then start again. Or try again, try my direct substitution again. So here we go.
And
so
just a quick shout out while you're doing that, because as you're getting them right, shout out to South Carolina for texting me -16 a couple minutes ago.
Oh, is that somebody who has the same initials that I do?
No.
Oh, okay. I know South Carolina.
Yeah, there's a lot of South Carolina.
Oh, is that somebody with an initial R?
Yeah, that's one.
Oh, how nice that she's watching. That she doesn't have to do that. Hi to South Carolina. Okay. All right.
Minnesota's watching too. We know. Hi, everyone. Yes.
Okay, so I took the derivative here while I was talking. Let's see if I can walk and talk at the same time. No, I cannot. Look at that denominator. That is
my
just
goodness.
horrible.
That's totally my fault.
Yep. Okay, so derivative of 5x squared in the denominator is 10x. Derivative here in the numerator, this derivative of square root of x plus 1 is 1 over 2 root x plus 1. And then derivative of the -1 is just 0. And then this is a linear term right here. This is like minus a half. So minus a half x like that instead of minus x over 2. So the derivative of that is just going to be the coefficient. So it's just going to be minus a half.
Yeah.
Now, as I look here and I think about, well, I'm just going to plug in 0 and try again. I think to myself, in the numerator, when I plug in 0, I get a half minus a half, so I get 0. And in the denominator, when I plug in a 0, I get 10 times 0, which is 0. So Lobethal's rule applies again. And I, even if I tried to do some algebra, I don't think it would help much. I think I'm going to go ahead and is this okay, Mark? I'm going to go ahead and do a 0 sandwich. Okay, so now let's.
What's in your sandwich? A whole lot of nothing.
Okay, so now I'm going to go ahead and do, hopefully third time or second time that I take the derivative, it'll be good. So derivative of the denominator is the easy part. So limit as x approaches 0 of the derivative of 10x is 10. Derivative of the numerator, well, the derivative of this negative a half is going to be 0, but the derivative of this 1/2 x, 1/2, whatever it is, I'm going to just put it like this, 1/2 of x plus 1 to the -1/2. So I need to take the derivative of that. So I'm going to go ahead and use some power rule. This ends up being -1/4 and then x plus 1 to the -3/2. How does that look, Mark?
That looks really good.
Okay, so -1/4 and then x plus 1 to the -3/2. I get a little nervous about this exponent here, but when I substitute in a 0 for the last time, it's going to be a 1 that I'm raising to the -3/2. So 1 to the -3/2 is 1.
It's
and
wonderful.
So it's wonderful. So I have -1/4 divided by 10, which would be fine to leave it like that, or -1/40.
Good.
And then the last one, those of you who are AP teachers out there might definitely recognize this question because it appeared on a recent exam. So let's take a look at this one. It's it could be it's a little different, always creative on the AP exam, in my opinion. I love it. But a little note says that f of 1 is 1, f prime of 1 is 2, and f double prime, or the second derivative of 1, is 3. So, okay, whatever, maybe that was given in a table or something like that. But so here's just some information. And now I have this limit. It's the limit as x approaches 1 of 10 to the x minus 3 f prime of x, all divided by f of x minus arctangent of x. And arctangent of x is just inverse tangent. Could be read either way. Could be written either way. Okay, so if I substitute in 1, in my numerator, I get 10 to the 1, which is 10, minus 3 times f prime of 1 is, f prime of 1 is 2. So in my numerator, I don't think I'm getting 0 here.
Nope.
I'm getting 4, right?
Yeah.
Okay, in my denominator, if
and by the way, just that means Lobethal's gone, right? Because that's not. That's.
Yeah, because only if it applies. You can't just willy-nilly be doing Lobethal's rule. Oh, I see a limit. Now I'm going to do Lobethal's rule. It's only if it applies. And it only applies, at least in our curriculum, in these two indeterminate forms. There's many, many indeterminate forms, but we're only responsible for these two.
Yeah, it's Lobethal's is a race to 0 or a race to infinity, and you're just comparing how fast they're going, comparing their rates. And this guy's not going to 0, so different game.
Different game. So let's see. In the denominator now, f of 1 would be 1 minus inverse tangent of 1. And inverse tangent of 1 is the angle, the radian measure, where the tangent's equal to 1. Tangent! Oh my gosh! The tangent, the guy at the beach. Okay, anyway.
He had a quarter of a pie.
Pi over 4 where the tangent equals 1, the ratio of the sine and the cosine end up being 1, so that would be pi over 4. So that's a really nice one that
And again,
appears that you might need L'Hopital's rule, but
that middle line is enough, right?
oh yeah, we can.
That's
put our
considered
smiley face
numeric.
here.
Yeah. Oh, nice.
That one's good too. Yeah. Okay. So that's just a little bit, and I know I'm going quickly, but just reviewing L'Hopital's rule from Unit 4. So Mark's going to finish off our new examples with one of my absolute favorite. I cannot believe I'm letting him
finishing.
do this.
I thought you were. Okay, this will be fun.
Oh, okay. Well,
no, let's go.
Okay, let's go. Actually, I have it right here.
I have it. For some reason, I know you love this problem. So.
I do. I love this problem so much. Hint, hint to my own students. Your quiz on Sunday is going to look a lot like this. I've been working really hard on making one kind of similar to it.
And hint to my kids. I proofed that already, so I'll steal it.
Yeah. Well, they're hard to write so that they come out properly. You need to have a good appreciation for the writers of these things, because for everything to kind of knit together perfectly is really beautiful. So anyway.
And this is in the Dropbox. It's also it's excerpted from 2017 AB6. We did drop a part off, but
yeah, because it uses mean value theorem, I believe, and we're getting to that next week.
So let f be the function defined by f of x is equal to cosine of 2x plus e to the sine x. Let g be a differentiable function. The table above gives values of g and its derivative g prime, so that's the table. And let h be the function whose graph, consisting of 5 line segments, is shown in this figure. It says, find the slope of the line tangent to the graph of f at x equals pi. And then also there's a b and a c, but I'm gonna do one bite at a time. I'm not gonna try to eat the whole 72-ounce steak at once. Slope of the line tangent to f at x. Well, that sounds
Was that a shout out to Amarillo, by the way?
A little bit. Yeah.
Big Texan steakhouse.
So we're looking for f prime at pi. So we're going to take f of x. So this cosine 2x plus e to the, sorry, I was thinking ahead already. It's a horrible habit. And all right, I'll take the derivative of the left side. I'll leave the rest as an exercise. No. Derivative of cosine. Negative sine of 2x, or the opposite of sine of 2x. And then I'm going to chain that 2 out front. It's not sine of just x, so a 2x chain is 2 at front. And then e to the sine x, well, exponentials just like to be themselves, but then not just an x, so a cosine x out front. And that's my derivative, as nice and cumbersome as that may be. And now we have to do f prime of pi, -2 sine of 2 pi plus cosine of pi e to the sine of pi. And let's see, sine of 2 pi, Verge, help me out on that.
0.
0, that's gone. Of course, this is numeric, but we're going to be using it in a second. So cosine of pi?
-1.
And sine of pi?
0.
So that is -1 times e to the 0, or just -1. Oh, and why didn't you tell me to scoot up?
No, it was good, and you were talking the whole time, so it's
okay.
Perfect. Yeah.
So we have the -1 times e to the 0, f prime of pi is -1. So that's my A.
And they didn't ask to write the equation of the tangent line. It just said to find the slope. So you don't have to then put it in an equation. Like when we did that one with the potato where we used the tangent line to make an approximation, we had to do a little more, but here it was just find the slope of the tangent line, or the line tangent.
All right. So let k be the function defined as this composition. K of x equals h of f of x, find k prime of pi. And my table on G is cut off a little bit, but we're just using h and f here. We're looking for k prime. Uh-oh, it's a composition.
Yeah, and remember, it is a composition. It's not a product there.
All right, so
yeah.
So we have to peel away the layers. We take our derivative of our outer layer and chain out the inner. And now I want K prime at pi. So I need H prime F of pi minus F, oops, times.
Mm-hmm.
Well, F prime of pi, that sounds familiar, Verge.
-1.
That was -1 in part
Mhm.
A.
Yep.
So we have a -1. F of pi, well, let's see.
I think I could do that mental math.
I think you can. It is cosine of 2 pi.
Yep.
That's
Which is
-1. No,
no.
0. That's 0. That's a full
Nope.
circle.
Nope. Nope. Cosine of
1. Well, it's the same as the angle 0.
yeah.
It's Friday. Coffee's just not doing it. All right. So I'm just going to go ahead and write it in now because I goofed it up. All right. So cosine of 2 pi is
Is
1.
1.
Sine of pi is 0.
Uh-huh.
So that's
So
2.
2. Okay.
So
Yeah.
that's 2. But now I'm not done, right? That's still sitting inside that H prime
Mm-hmm.
times -1.
Mm-hmm.
And H prime at 2. Well, I have to come up to my graph. Looks like the tick marks are marked. So here's 2. And that's not a real easy point to read. But what is that point?
Well, I don't think we need
That's
the point.
actually H, right? That's H of 2.
Yeah.
And we want H prime. So we just want the slope of that segment.
Yep.
And it looks like it goes down 1, right 3.
Mm-hmm. Nice.
So K prime at pi is 1/3.
Mm-hmm.
And I hope you're checking me on these.
I am. You're doing great.
All right, on to C. And I'm going to get a fresh piece of paper for that.
So for B, you guys, just it was 1/3, just so you know, because he did kind of whip his paper away quickly.
Oh,
but
I'm
just,
sorry.
No, it's fine. And by the way, we know we're going a little over, and we asked our producer if we had permission to do that. And so we'll just play like it's regular high school, and let's pretend that there's so many situations where they hold the bell. I don't even want to say what they are.
Yeah, let's not go down that.
Am I right, Mark? Like,
yes.
Could they ring the bell already?
Okay, here's
we have been so good about sticking to the 45 minutes though on our AP lives, and our producer
keep talking. Said, I'm doing some origami over here.
That's fine. Our producer said it's fine if you go a little longer than 45 minutes, and I said I really wanted to, going into this weekend, make sure that we did all of the wrap-ups that we wanted to. Wow, that was slick.
Thanks. That's a lot of Mad Magazine fold-ins at the back for the older crowd. Okay, so now I can see everything. And look how nice they were. I was actually noticing this last night because we had our warm-up yesterday and it didn't have the dot. And we said it would have been so much nicer if we'd put the dot into that product. And they did.
Yeah, because this is actually from an AP exam. This is from 2017. So, I mean,
we're trying to find.
Yeah, we're trying to find m prime of 2. Yeah, so we need to take the derivative.
So the derivative, and I guess I'll use the traditional as you take the first function times the derivative of the second, which is just h prime of x, plus the derivative, we're going to chain out a -2 of this g prime of -2x times h of x. And now we want to evaluate all of those at 2. So I'm just going to, everywhere I see an x, kind of substitute in a 2. And now I can scoot this up because now I'm just playing off of these, right? No F in this one, right?
No F. This is even better.
Just going up to the table. So, so -2 times 2, -4. When x is -4, g is 5. H prime at 2, well, we just did that, right? That was the -1/3.
Yep.
Now, -4 again, g prime of -4 is -1. Oh, I do need that H of 2.
I got
But-
you back. I got you
Hey,
back.
I'm going to do it this way. If the
Okay.
slope is negative 1/3, the slope is also negative 1/3 for every 1 unit over.
Mhm.
So down a third, down a third. That's negative 2/3.
Yep. Or as you say, negative 2 turds.
2/3. Yeah. I start that at the beginning of the year, and I still think it's hilarious in May. Not sure everyone else is on board with me, but all right, and we can leave it, right? We can walk away.
Yeah, walk away.
So, of course, we can't because we're math people, but is that just, wow, that works out nice. Is
I
that really
know.
just -3?
I think so. Yep,
Wow.
it is.
But that is a perfectly reasonable way to write -3 on a timed AP exam.
Mhm. Yep.
All right. So
we did everything that we wanted to do. This is exciting because we're good, and we're going to just talk a little bit about what's in that shared folder besides the Lobethal's rule notes page and besides the free response questions. What else can they find?
well, here's the bit.ly and the QR code that'll take you right to that top level of that folder. You'll find the schedule on the top level, and then in the unit, the mixed bag 1 through 4, it has the date on it, April 17th. You're going to find the free response we did today as far as the funnel and the mixed representation. Again, that potato problem was in yesterday's folder. It was the end of that document. You're going to find a circuit written by Vicki Carter out of South Carolina.
Oh my gosh, it's so good. It's one of my favorites.
Yes, and it's really cool. It has a table at the back, so it brings in all this stuff, and it's got some chain
and a
rule in it.
graph, I think, too,
Yeah,
right?
it's nifty.
Yeah.
And
really
the Lobethal worksheet that Verge had been working through is in there as well.
Mhm.
And Wednesday, what did we do Wednesday?
Chain rule.
The key to the notes from Wednesday was put in the Dropbox this morning, actually. So that's in there as well now. So
Okay. Good. Well, we hope everybody has a good weekend, whatever that means. I mean, and we know that that's what we usually say to people on Fridays, but hopefully you can find some time to watch a movie or something. I don't know. We have a movie night planned for tonight for our family, so I'm looking forward to time on the couch.
Yeah, well, my wife has never watched through Parks and Rec, and I think we're in season 5 or 6 now. We started it last week, so.
And you're in the office, not in the
what
office.
inspired
You're
that's what
in the
inspired
Parks and
today's
Rec office.
background. Yes.
Yeah. Good. Enjoy. That's
Ron,
some good
Ron,
stuff.
Ron Swanson is a wonderful human being. All right. Thanks for
Bye,
watching, everybody.
Thanks for watching us. We'll see you Monday.